Hello and welcome to Calculus1. This is part 2 of our lecture on graphing function by hand. As I said in part 1, I believe, it is something that we can easily achieve with technology today, right? Computers and calculators and graphing calculators and all that stuff. No issue at all. You can also achieve it easily by using the middle school method, which is pick x and compute y's, plot those dots, and connect the dots, like in a coloring book. But the problem with that method would be that you might run into a situation where the interesting thing that is happening with the function is not in the range of points that you picked, right? Because you have to pick some points, and let's say generally you pick like between -2 and 2 or -10 and 10 and so on. And what you're going to do if the interesting stuff is happening at x equals 20, right? So it's a very inefficient method, right? So we would like to develop a technique to graph anything by using calculus and things you learned before. So what we came up with is the list of these 13 things disguised in 8 bullet points, where you look for domain, you look for x and y intercepts and 3 horizontal, vertical, and slant asymptote, get the first derivative, so first, second derivative tests, and then if you need additional points, like that's the middle school stuff, to put all of the stuff together. So we started this last week. We already completed the 2 problems, right? We started with a very simple problem on polynomial, x cubed minus x, and we found all of the things from the list, and then finally compile the graph. Now, when you are drawing this graph, you are supposed to get the points and asymptotes first, and then after that you go and look at increase, decrease, concavity, and so on to fit in these curves. So now we are going to take a look at some of the problems that are, 2 problems that are more advanced. So we did that one, and then we did this one, which is a rational function. And for the rational function, you know that if the degree in the denominator is by 1 less than the degree in the numerator, you have a slant asymptote, and the only way to get it is to use long division. So that's exactly what happened. We had a vertical asymptote at -½ which is what breaks the domain at -½ and then we also had a slant asymptote at some 1/2 x plus 1/4. So we did all the calculations. Yes, the derivatives were very interesting. That's my choice of words. First derivative test, second derivative test, all interesting. And then finally the graph, right? And again, we draw all the asymptotes, we draw all the points, and then after that we just snake the function through. No one cringes on the word snake? That's good. How about spider? Anyone? No? No. Because you know what would happen, right? Oh, I don't like snakes. Oh, I don't like spiders. Exam 3. A snake is chasing a spider. At the rate.
Instead of a spider, you just have snake for
Oh, the screen. Yeah, 1 year I put Darth Vader. It was so funny. One of the students went, whoa. Because it started with puppies and cats, and eventually I switched. Yeah, it's you know, it's for you to, you know, to relieve your stress, but also for me, because it's excruciatingly painful watching you do the test. You have no idea. Let's do something that is not the test. Wow, this is a lot of wonderful problems. Do you have any favorites? I don't know. Look at this. Wow. We have trigonometry, we have ln, we have radical functions, exponential. Wow.
Someone picked the easiest one. 30, I think.
Which one?
30.
Problem 30?
That's LM.
X squared. Well, thank you. This is like a gift. He's like, here. Do this one. Can I do this one eyes closed? Yeah, I can. 30. Lock the doors. G of x is x squared ln x. Perfect. We start with number 1, domain. Domain is 0 to infinity because ln x is a restrictive one, right? X squared has all real numbers and ln x has only positive numbers, so that's the restriction. Number 2, x-intercept, we set y equal to 0, and we want to calculate x. Well, when we say x squared ln x equal to 0, we use the zero product rule. It's x squared equal to 0, which gives x equals 0, but we have to throw that away. It's not in a domain. Not in the domain. There we go. And then we have also ln x equal to 0, and that happens when x is equal to 1. You can e both sides too if you don't know that. So yay, we have 1, 0 as the x-intercept. Now for the y-intercept, we set x equal to 0, but that's not in a domain. So plus we also know that x equal 0 is the vertical asymptote for ln. Anyone? This is really good. 5,000 people are shaking their heads. Yes, we all know. So it's for the stream. So number 3, vertical asymptote, clearly x equals 0 because ln x, right, has the vertical asymptote there. Horizontal asymptote, none. Slant asymptote, none. Right? We don't have. Slant asymptote only happens when you have polynomial divided by polynomial if the degree on top is by 1 higher. So that's that. Number 4, shall we take a look at some calculus finally? First derivative is going to be copy the first derivative of the second plus copy the second derivative of the first. Nice. This cancels. Factor out x, and we are left with 1 plus 2 ln x. Nice. So I have my first derivative. So f prime of x is equal to x 1 plus 2 ln x. Again, it is factored. We need it to be factored so that we can set it equal to 0 for critical points. Coming up soon to the theaters near you. F mentioned theaters. Went to see The Incredibles 2. It's incredible. The next one is take the derivative again for the second derivative. So copy the first derivative of the second is 2 over x. Plus copy the second, which is 1 plus 2 ln x. Derivative of the first is just 1. Nice. So what is this now? Second derivative over here is going to, this dies. Actually, we can do it here. So 2 plus 1 plus 2 ln x. Oh, nice. So 3 plus 2 ln x. Beautiful. All right, so we are going to box these puppies so we can find them quickly when we need them. Now we go and figure out first derivative test, right? So for the first derivative test, we need the critical points first. That was your lecture 4.1. So we set x 1 plus 2 ln x equal to 0. We get x equals 0, we have to throw it away. I'll just write domain, and you know what I mean. And then we have 1 plus 2 ln x equal to 0. ln x equals to -1/2. Well, when we e both sides to solve this thingy, we get that x is equal to 1 over root e. Nice. 1 over root e. So, let's partition. I have 0, which is the vertical asymptote. I have nothing to the left of that 0 because there is no function there, right? So that space doesn't exist. We only are looking at positive numbers going to infinity. That's our domain. So you have to make sure that you have only the domain represented in your partition. And then we have 1 over root e. Now you'll be computing in the first derivative, which has ln x. So you should compute on e's, right? So the cool test points should be 1 over e and e. Now why is 1 over e a cool point? Well, first of all, when you make denominator bigger, you make the entire number smaller, right? If you have a cake, well, then you have one whole cake. If there are other pests around, then you have less of a cake, right? So denominator just became larger, right? Because there are more people. So you have, in this case, increasing the denominator. Now, clearly e is bigger than the root e, so 1 over e is a smaller number than 1 over square root of e. So I'm using that to find numbers that will be easy to compute in my first derivative. So 1 over e. And the derivative is x. So that's going to be 1 over e. And then 1 plus 2 ln 1 over e. How much is ln of 1 over e? Well, that will be ln of e to the minus 1, and then ln of e is 1, so the whole thing is positive times a negative. Again, this term over here is a negative term, so it makes a negative 2, right? Maybe I should write, that's a negative 1 right there. So the whole parenthesis is negative 1, and then positive times negative, that's less than 0, it's a decrease over here. Now, the second derivative at e is going to be e 1 plus 2 ln e. Now, that's going to be e times 3. That's positive times positive, which is larger than 0. And we have, boom. What is free for us is to know that at our critical point we have minimum. Thank you, Abby, for being this. So we have a minimum here. Now I want to know the y coordinate for that minimum. And that's going to be 1 over root e ln 1 over root e, squared over here. So the y component of that is 1 over e times negative 1/2. So it's negative 1 over 2e. So minimum at 1 over root e, negative 1 over 2e. That's where the minimum is. And I'm going to box that because that's one of the things that goes on our graph. Number 6, I guess. Second derivative test. Please be 6. Yes. I have the second derivative, which was 3 plus 2 ln x to set to 0. And what we get is that the negative 3 divided by 2, right? So that's ln x equals to negative 3/2. And if that's ln x equals negative 3/2, well, e both sides, we get x equals to the e to the negative 3/2. That's the inflection point. Inflection point. So my partitioning, again, has 0. That's the vertical asymptote. And we have e to the negative 3/2, which is inflection point. And this thing is going to infinity again. Clearly, e is a good choice, because that's going to be larger than this. And then 1 over e squared, because you have this guy is 1 over e to the 1.5. Right? 3/2 is 1.5, and it's negative, so it goes in denominator. So what's bigger than 1.5? Well, 2. Also 3 and 7, but 2 is just good enough. So by making the denominator bigger, we are making the number smaller. So 1 over e squared is a good test point for us. Now we do the second derivative test by plugging these test points in the second derivative. So second derivative computed at, I can put e to the minus 2, that's what it is. We have 3 plus 2 ln e negative 2. Negative 2 jumps out in front, makes a negative 4. 3 minus 4 is negative 1. Less than 0, concave down. Second derivative of e, well, that's 3 plus 2 ln e, which is equal to positive 1, bigger than 0, concave up. Nice. Do I need additional points? No. Hopefully not. 7. Hold on. If we need it, we'll come back. To draw this graph, I'm going to focus on the domain part, which is 0 to infinity. I have a vertical asymptote at 0, right? We know that. And then we have some of these points. Let's see. There it is. We have x-intercept at 1, 0. What I'm going to do is I'm going to put 1 at 4 units. That's 1. It's x-intercept. The graph has to go to that point. Then I had another point here, minimum, 1 over root e, negative 1 over 2e. 1 over root e, negative 1 over 2e. All right, so you can approximate this. We can also take a look at the decimals, just to make it more precise. Let's use the calculator for these things, but again, you should be able to approximate. You just use e is about 2.7. You know, a little bit of stick in the sand, and just, you know, wave a little bit, and you get. So 0.6 on x, and then we have what is this? 0.5 times e negative 1, about 0.2. Great. So 0.6 on x, which is here somewhere, and negative 0.2. So this is where our minimum is. So it needs a smiley there. And I hope you see that it will actually go through this. So, this is going to be a very interesting graph. Nice. Concave up, concave down. Okay, let's see what this is. Oh, we didn't compute the y coordinate for inflection point. So we have e to the negative 3/2 as x. To find its y, I need to go e to the negative 3/2 squared ln e negative 3/2. I don't need parentheses. So for the first one, it's just e to the negative 3, because 2's will cancel. And then over here, negative 3/2 goes in front, and then ln e is 1. So the inflection point is at e negative 3/2, comma, negative 3 over 2e cubed. Nice. And the decimals for this, it's never-ending fun. X coordinate is about 0.223, but yeah. And then we have a negative 3. Oh, let's call on. That's negative 1.5 divided by e cubed. Oh, perfect. Negative 0.7. No, negative 0.074. So that's that. So inflection point is somewhere over here. Nah, that's on axis. Undo, undo. So what does it say? Concave down, concave up. Okay, so now we need to connect this and then we're done. Connect it like that, but let me see. Concave down up to, okay. Wow, this problem is insane. So that would be the behavior there, and over here we have a concave down with this going into the 0, 0. You see, limit is 0. So the graph is trying to go to 0, 0, but because it has a vertical asymptote, it doesn't have a point there, so we have to put the open circle. You can limit of g of x as x goes to 0 equals 0. You can try this limit and you will see that that's what we get. Now we'll talk more about this maybe on Wednesday, I believe. So a limit like this will come up. Well, that was a great pick. Wonderful. Let's see if you can do worse. Anyone? I mean, if you're not picking anything, then we can just move to the next lecture and you can figure out the rest on your own. Anyone? All right, the next lecture, I guess. We still have time. I still didn't turn it off. I'm going to. I guess next lecture. All right, fine.